Get started. Hi, Natalie. The slides. And let me try to use this spotlight, if that helps. Do you see the spotlight? Yes, okay, good. So let us get started. So first of all, the midterm week. So thank you for filling up the doodle poll. And the best week turned out to be from February 26th to March 5th, namely the next week. So today I'm gonna post the new homework problem. So that's the regular homework. But next Friday, I'm gonna post the midterm problem. And it's take home, week-long, open book. So you can use all the material from B courses, your own notes and the textbook as well. But you have to sign an honor pledge that you are not getting any help from human beings. So for homeworks, I really encourage you to work together, but for the exam, that's all by yourself. So that's the big difference from the regular homework problem, but that's the format. And I believe this is the way of minimizing sort of pressure and burden on you. And of course, I have to put trust in you that you're not actually doing that together, but I do put trust in you. So that's the idea. Any questions about the midterm? Everything clear? Okay, all right. So now we go into superfluids. So what we have done on Wednesday is to come up with an argument why dealing with a classical field makes sense, even though we are dealing with highly quantum state of matter, namely Bose-Einstein condensate. So to the extent that you study perturbation theory in a dimensionless combination of the self-interaction, chemical potential, and the mass of the particle, of course, together with h bar, as long as the combination is small, then you can trust the perturbation theory. And the lowest order perturbation theory turns out to be exactly just solving the classical equation of motion. So that's the idea we talked about. That's really the manifestation of this wave-particle duality. And once you have a quantum system, then there are different ways of taking classical limits, and BEC happens to have a good classical limit in classical field theory, and that's why we are studying field theory. At least that's one of the reasons. So now that we know classical field theory actually makes sense, we'd like to apply it, and then we discover that they actually turns out to be a superfluid, namely an extremely weird kind of fluid that flows without any friction and viscosity. So that's the idea of the superfluid. And I have shown this slide already actually last week. So if you put this Bose-Einstein condensate in a tube like this, so you put this basically in a circle, and I ignore the thickness of this tube. And then the obvious thing to do is switch to polar coordinate. So this is on XY plane, so forget about Z. And once you switch the polar coordinate, you have R and theta, but I'm ignoring the thickness of the tube, so R is now fixed. So the only variable in this differential equation is theta, so that is a big simplification of the problem. So now psi, a classical field now, is a function only of theta, that's the angle on this plane, and time, then you have time derivative over here. And what it means though, is that once this is the function of the angle, because angle is periodic in 2 pi, the psi should be a periodic function of theta. And that actually gives you an interesting quantization condition. So first of all, I ignore R derivative because I'm ignoring anything in this radial direction, 0 thickness, R is completely fixed. But now you have imposed this condition that is periodic in theta. So the only theta dependence that can appear as a solution is an exact solution to this field equation, even though it's nonlinear, there's an exact solution, is e to the I n theta, where n is an integer. If n is not an integer, then this wouldn't satisfy this periodicity condition when you go from theta to 2 pi. So this n has to be an integer. So there's some quantization condition happening here. And once you put this e to the I n theta, this dd theta becomes in. So this becomes n squared of r squared. And in order to satisfy this differential equation, time derivative would pick up this combination h bar squared, n squared over 2m. That's precisely this combination that appears in the exponent for the time dependence. In normalization, this square root of mu minus mu over lambda is something you already looked at already, namely that this actually balances off the last two terms in this field equation. So in order to have negative mu psi plus lambda psi dag of psi canceling against each other, that fixes this normalization to be square root of mu over lambda, which has the meaning of the square root of the number density, because psi dag of psi is a number density. So then you find this exact solution to this classical field equation. So now we'd like to know what this means, right? So we justified classical analysis in the spirit of perturbation theory. So we now put trust in the solution we just discovered. So the question is, what does this solution physically mean? And that's the next question we'd like to answer. And what helps us understand this better is look at this current. So now the psi is a field. Psi dag of psi is the number density. You can also talk about how the number density move with time, and that is the current. And you have seen this kind of expression in quantum mechanics when you look at the Schrödinger equation and define the probability current, I believe. So this is the same expression. It turns out that now that psi is not a Schrödinger wave function, but it's a field now. This ends up having the meaning of the current of particles flowing. So psi is no longer a probability wave, but the wave in the real space, which describes the density of the particles. This describes actually the current density of how many particles are moving at a given position with what speed, namely the number density rho times the velocity is this current. Okay, so this current then can be worked out very easily with this the explicit solution to the field equation. I just plug that in here. And you have theta derivative here, so that will pick out n from the exponent, and then put all the factors together, then you find this expression. And what you notice is that mu over lambda is nothing but the number density. So the rest, nh bar over mr, should be the constant speed in the theta direction. So now we have an interpretation that this solution describes Bose-Einstein condensate flowing in the theta direction, basically circling around in this tube because of the constant speed. So now we are talking about real fluid, right? Because this is something that's really flowing. But interesting thing though, is that this fluid has this velocity that is quantized in certain unit by an integer multiple n. In particular, people define this quantity called v dot dx. This is what you define in fluid mechanics called circulation. So this is how much velocity there is, and you integrate this over this entire circle. Then you find that this is quantized in the unit of h over m. And h is, of course, a 2 pi h bar. 2 pi comes from theta integral together with h bar that turns into Planck constant h. And h over m is certain quantity defined in this fluid once you know the mass of the atoms in the system. And the circulation turns out to be quantized in this unit of h over m. So this is actually a weird situation, right? You're talking about fluid flowing in this tube, but you can't have an arbitrary velocity. It could be static, so you can have a fluid that's not moving. You can have a fluid that's moving with n equal 1, n equal 2, n equal 3, but not in between. So fluid velocity is now quantized. It doesn't come with an arbitrary number. It's either 1, 2, minus 1, minus 2, but it's always integer multiple of this quantity h over m. So this is actually a quantum of the circulation of this fluid. So what that means though, is that because n is an integer, once you have a fluid moving with n equal 1, normally you would think that the fluid would have a friction with the wall of this tube. It may have collision within the fluid, and that the fluid actually has a viscosity, so eventually would slow down and slowly stop. That's what you would expect. But that cannot happen here because n is either 1 or 0, never a half, never 0.35, never 0.879. So it cannot gradually go from 1 to 0. And if you can't do that, the only conclusion is that this fluid has no viscosity, no friction, just keeps flowing with a permanent velocity. And that is the idea we call superfluid. So super in this case means it has zero viscosity, zero friction, keeps flowing. And that is what this is called, a persistent flow. Persistent meaning just keeps going forever. And that's the idea of the superfluid. Any questions about this argument here?
I have a question.
Go ahead, Cameron.
I was wondering, with this like quantum circulation, does it have any connection to like the Sommerfeld like quantization, like as part of like the old quantum theory, or like
It certainly has relationship because this really looks like p dot dx if you multiply with m, right? So
right.
mv is p dot dx, then this m is canceled. It's really integer multiple of the Planck constant. And that looks basically exactly the same thing as Sommerfeld quantization condition. But here we are not talking about point particle though. This v is the velocity of thousands or millions of atoms flowing together, and yet it satisfies the same condition. And that's again because of this resemblance between the Schrödinger field, which describes a system of many, many particles, to a single particle Schrödinger wave function, which describes only a single particle, but they look similar. And that's why you end up having the same quantization condition. But the meaning of this is totally different. We are talking about thousands or millions of particles flowing together, yet the momentum is quantized and it leads to no friction, no viscosity. That's a very weird situation, that unlike any normal fluid we normally actually observe. So even though mathematically they look similar because of the resemblance of the Schrödinger equation and the field equation, the meaning is very different. Does that answer your question, Cameron?
Yeah, it does. Thank you.
Okay, great, great. Any other questions here?
Oh, I have a question.
Hi, Geraldo. Go ahead.
Is it possible to change like from a certain n value to a different n value?
That's an excellent question, and that's the next slide. So that's going to come up in a second or so. Great. But this is a great class. You always ask great questions, Adi.
So is this like a quantum system where if you observe it, it collapses to a certain n value, and has like certain probabilities of being in a certain quantized velocity? Or is
so that's what will show up in the next slide too. But the basic idea is that when you make Bose-Einstein condensate in your laboratory, and if you actually start with sort of rotating fluid and put that in this sort of the tube-like potential well, then it ends up circling, and then you see the picture of that on the next slide. So you see that too. Excellent. You all anticipate the next slide. But just to pause this here for a second, I actually made an outrageous claim, right? So we use this classical field theory. I solved this and found that there's a quantized, this integer, the quantum number. And this is something called also topological quantum number, because this n tells you how much phase would change by going around the circle once. So by going around the circle once, theta goes from 0 to 2 pi, this field equation, field, which changes phase n times. So 0 to 2 pi n. So this idea is that when you actually have a circle, and imagine that you put this circle like a rubber band and put that on a bottleneck, then you can either put it with one winding, twice winding, 3 times winding, and so on and so forth. And that has to do with the topology in mathematics. So on the continuous deformation, it doesn't change, but all you can do is really create a jump. And if you think of the infinitely long bottleneck, that would never change. So that is what gives you some extra stability to the system because it cannot change continuously and hence no viscosity. So that's an outrageous claim I'm making about the physical systems, but it is justified because of the nature of this topological quantum number, in this case called the winding number, of how many times the phase would change when you circle around this the tube. So that's the beginning of this idea called topological protection of the state, which is now a very popular idea in condensed matter physics. Okay, any further questions here? Then I jump into the pictures and how you actually make this kind of thing. All right. So here's the picture. So this is the potential well these experimentalists have created. They call this a toroidal trap. And you put all these cold atoms in this trap. And you have seen the video how you actually cool the system from the NASA. And then you eventually form a Bose-Einstein condensate. So this is actually before forming Bose-Einstein condensate. It's still kind of jagged. But at the end of the day, you either form a condensate which is not circling, then spread out without hole in the middle, or condensate with non-zero n. I don't know what n is for this picture, but this n shows the fluid is spread across this tube-like potential well, and with finite n. So this is actually flowing either this way or that way, I don't know. So you can really make this kind of the fluid where the Bose-Einstein condensate is flowing without any viscosity. And that gives you this topological protection. And one thing I did mention, I believe last week, is that Bose-Einstein condensate itself is actually not forever, because when atoms come close to each other, we are talking about this incredibly low nanokelvin temperature. So either rubidium or sodium would like to become a solid at that kind of low temperature. So namely, the atoms will start to stick together and eventually become a solid. So it doesn't last forever. Only when it's sort of an infinite thin, you can avoid that situation so that the Bose-Einstein condensate would stay BEC for a long time. So there's always this issue of possible instability. And once Bose-Einstein condensate is lost, then description using classical field is also lost. And that's when you can see the friction and viscosity and the system would collapse. And that's what you see in this picture. So if we have Bose-Einstein condensate, which is this picture here, without circling around, then it starts to decay and you lose BEC. But if you have a BEC with non-zero n, it lasts for quite a while. Quite a while in this case is only like 10 seconds, but this is actually quite a long time from the point of view of moving atoms, because it's moving, as I said, pretty fast in this condensate. So this is actually a stability guaranteed or protected by this topological quantum number. Now that n is 1, presumably, then it cannot slowly decay. It has to jump by tunneling to 0, and then becomes, you lose the BEC. So that's why it is protected for a much longer time than a condensate without this kind of topological protection. So this D picture would last a lot longer than C picture over here. And that's the evidence in this data that there is definitely a topological protection of a quantum system with this topological quantum number. So classical field theory analysis is still very good. You can find a non-trivial exact solution to the field equation. And at the beginning, we didn't know what actually meant, but now we know what it does. So this is meant to be a fluid flowing inside this tube in a circular fashion with a constant velocity and has this integer quantum number. An integer cannot gradually decay. So we predicted that will give you a persistent flow with no viscosity and no friction. And indeed, you can make such a system in the laboratory. And that system is topologically protected. It lasts for a long time compared to the state which does not have topological protection that would quickly decay away and you lose BEC. So this is showing basically two things at once. While it's being stable, this is circling around with constant velocity, which means you literally observe a state with zero viscosity, no friction, but it still does decay because when the atoms come close to each other, they start to stick with each other, solidifies, then you no longer have this amazing superfluid. So it does disappear at the end of the day, but having a non-zero momentum with this non-zero topological quantum number, there is a protection. The state is much more stable and protected against this decay because of topological quantum number. Again, let me pause here. I hope I address questions by adding Gerardo, but if you have any further questions, just fire up.
Would it be possible to increase the N number of this rotating superfluid so that you
Yes.
can maintain the stability of each? Okay.
Yeah, but it could actually lead to something interesting though, which is the idea of vortices I'm going to talk about next. So in this case, I'm not putting a system into this donut-shaped tube. This is still in the bucket or some potential well, but I can still rotate the fluid. Then ask the question, what would happen to it? So in this case, you can have a situation basically with n equal 2, but then system would break up into 2 parts, each with n equal 1. And that is the idea called quantum vortices. So let me talk about this and get back to you, Earl, so that you can ask more questions about this. So what is the quantum vortex? So I already mentioned this idea of topological protection. And here I'm just using a mathematical notation for it. So in this case, you have a symmetry of changing the phase of psi, which is called U1 symmetry. And if you don't care about the group theory mathematics, you can totally skip this part. I'm just trying to make connection to the idea of topology, namely algebraic topology, just in case you want to know more about it. And so the changing the phase of the wave, the field is what is called the U1 group, namely that just the phase is a 1 by 1 matrix. So that's 1. And phase is unitary because once you have a phase in its complex conjugate, they are inverse to each other, they multiply to 1. So that's the definition of the unitary matrix in general. So this is the one-dimensional unitary matrix. That's the phase of the field. And one-dimensional unitary matrix, because it's just a phase, it's the same thing as one-dimensional circle. So the mathematical notation S1 is this is one-dimensional sphere, S for sphere, just a circle on the plane. So U1 is a symmetry that can act on this field psi, namely you can change the phase that forms the group called U1, 1 by 1 unitary matrix. But topologically, this group has a shape of a circle, so that's this S1. Then you ask the following question. When you go around this tube, that's also a circle, you can ask the question, how does this circle, namely space in this tube, would map onto the space of the field psi, which is described by this U1. So you are looking at the map from circle in space, which is this tubular shape, onto the space of the field, which is also a circle. And that's the situation I mentioned, like putting rubber band on the bottleneck. So around the bottleneck, you find a circle, and you are mapping a rubber band on top of this circle around the bottleneck. Then you can classify this kind of map according to how many times you wind around it. And so this is what is called the winding number. And this is given by what is called the homotopy group pi1, which tells you how you can map a one-dimensional circle into a space. And this target space is, in this case, the one-dimensional circle. This is a space of this field. And then this is the map from S1 to S1, which you can classify according to how many times your rubber band wraps around this bottleneck. So this is just a mathematical language for it. And this is has a very rigorous mathematical definition. It turns out that what we have just done of having this n as the topological quantum number has to do with this idea called a homotopy group in algebraic topology. But as I said, if you don't care about this mathematical language, you can totally ignore this. Only when you are curious about this, you can look up this literature in mathematics to make a connection there. So if you're actually looking into a bucket instead of this tubular shape, what we are looking for is a solution to this field where the field approaches the minimum of this potential. And this is the potential once again. You need to be at this bottom, this potential. So the field value is fixed to V, which is square root of mu over lambda. But there are infinite number of minima in this potential. So when you go to spatial infinity, you would like to approach the minimum of the energy, but it can point to any phase of this minimum of the potential. So you can look for a solution where all the fields approach to V at infinity with the same phase, which is kind of relatively uninteresting solution. But you can also try to think about a solution where psi approaches infinity with the phase circling around again with this non-zero winding number. Is there a solution like that? And that's the question we ask here today. And indeed there is. It turns out that this nonlinear equation doesn't allow you to have an analytic solution. So you have to actually do this numerically, unfortunately, but you can do it. Then you find a solution that looks like this. So psi actually vanishes at the origin. So there is no condensate at the origin, but it would quickly approach the minimum of the potential. And this is the modulus of psi, so absolute value. And on top of this modulus, this actually circles around in phase when you plot it. So it actually looks like this. So you find the current psi given by this shape, V times e to the I theta at infinity, that gives you, again, a constant flow, which is the same form as you have seen with the n equal 1 for the case of this donut-shaped tube, right? So this is e to the in theta. Here I'm taking n to be 1. So you have a constant flow. But at the origin, because psi vanishes, the current also vanishes. And this phi is the same thing as psi, except that I absorb this h bar over 2m into the definition of the psi. So there's basically no physical difference between the two, just a difference in unit here. So you have the situation that there's no current at the origin, but there is a flow which circles around the origin in the same direction everywhere. And that is actually also a solution to this classical field equation. And now you see the reason why this is called the vortex. And we are suffering a lot from polar vortex these days. And that's one of the vortices in fluid mechanics. This is another vortex, now with a superfluid. And you can certainly find a solution like that by solving this classical field equation. So unfortunately, this is not an analytic solution. That's why I can't show you the form, but at least I can show you the numerical result. And this numerical result coming from the field equation, namely Euler-Lagrange equation coming from this field theory Lagrangian, looks like this. Then corresponding flow on the two-dimensional plane looks like this. Then you can indeed see that this is a form of vortex. And energy of the whole vortex is log divergent, the log of the size of the system. So if you have a vortex and also anti-vortex somewhere, then they actually attract each other with a logarithmic potential. If you have only one vortex in the system, then the energy of the whole system goes like log of the size of the system. So it's nominally log divergent, but of course, when you create a system in the laboratory, you got the finite size at the end of the day. So log divergence is actually not really divergent, but it grows only mildly as a function of the size of the system. So that's the property of this of the solution. And once again, when you compute this circulation, then it is indeed quantized, exactly like what we have discovered in the case of this fluid in the tube. And fluid in the tube was an easier problem because you have the fixed radius. You're basically looking at one slice of this solution where psi was indeed just exactly V. That's why we could solve this analytically. But now you put the system in a whole bucket, then you need to solve the solution for the entire space. And then you can't do this analytically anymore, but you do find a well-defined solution of this vortex. And it turns out that you can indeed create Bose-Einstein condensate with these vortices. But then I go back to the question from Earl, when you have this fluid with n equal 2, it turns out that vortex and vortex would repel each other. I mentioned that vortex and antivortex would attract each other, just like opposite charges in electromagnetism. But vortex and vortex would repel each other, again, just like in electromagnetism. So it becomes energetically favorable for two vortex, which is basically two one vortices bunched together, to separate into two separate vortices, each is n equal 1. And that's the idea you can see in the data of BEC with vortices on the next slide. But before going there, are there any questions about this discussion over here? Again, all we are doing is just to solve the classical field equation, which is nonlinear, non-trivial, but you can do it in your computer. Then you find this vortex solution to the Euler-Lagrange equation for the Schrödinger field. I'm sure there are questions. Don't be shy. Is it okay? Maybe it's easier to ask questions after seeing the pictures then, and I can always come back. It looks like this. So this is the picture of BEC with one vortex. Now, once you start with 1, 2, 3, 4, 5, 6, 7, n equals 7 BEC, then this would break up into 7 vortices, each with n equal 1. And each pair has a repulsive logarithmic potential. So each vortex would like to maximally distance from each other, so they are socially distancing. And maximal distancing on two-dimensional plane turns out to be a triangular lattice. So they start to form really regular triangular lattice. And that becomes even more clear once you go to larger and larger n. And here, this is a beautiful triangular lattice in a hexagonal pattern. And that's really just a consequence of this repelling force, logarithmic potential between the pairs of vortices. So big N doesn't stay that way because each vortex would like to sort of spun out into individual vortices to minimize energy. And to minimize remaining repulsive potential, they neatly line up into this hexagonal array, triangular lattice. So that's how you can understand what's going on with this vortex solution of the classical field equation. So now I believe things make sense. So any questions about this?
I have a question.
Go ahead, Riley.
In the previous slide, why did we take the limit as r of r approaches infinity?
Oops, where did it go? Sorry, I've done something wrong. Yeah, so that's a good question. So I took this ansatz because I don't want my system to have very large energy. You are looking for something relatively stable and therefore low energy. And when you go to the infinity, when psi stays somewhere on the slope of this potential, that will cost you energy difference between being on the slope versus being on the bottom, going like the area of or volume of the system. So that kind of solution would end up having a very large energy, and we expect those solutions to be unstable to lower the energy. So I'm anticipating that already. So if you go to large radii, you want to actually stick to the bottom to make sure that your energy doesn't grow linearly with the volume. And I told you in the end, the solution ends up being only logarithmically growing as a function of the volume. So that's actually not a huge energy, even for relatively large size. So that's how you find a solution which is stable, so that energy is sort of minimized already from the beginning. So hence this condition. Okay, does that answer your question, Riley?
Yeah, that makes sense. Thank you.
Okay, good. Any further questions on this? And I hope you appreciate that this is an amazing thing. So for each vortex, again, the flow goes on forever without any friction or viscosity. And that's how you see these pictures of the very neatly arranged triangular lattice. Of course, there is an instability at the end of the day for any BEC, they bunch together and solidify, but this can last for a long time, again, protected by topology. So that's really the evidence of this superfluidity, and you see these vortices, and this is indeed very beautiful picture. Just remind yourself, this picture consists of millions of atoms in it, and they're working together to create this very neat picture of the neatly arranged triangular lattice of vortices. And that's what's going on. And everywhere around this each blue point, then you see the fluid actually circling, flowing in circles. And again, of many, many atoms working together. And that's because of this is a Bose-Einstein condensate. Every rubidium or sodium atoms are identical particles, and they bunch together to form a classical field when the de Broglie wavelength is bigger than the average spacing between the particles. You have seen this animation, I guess, last week, when you go cool the gas, then each atom would start having a longer de Broglie wavelength. Once they start to overlap with each other, the whole thing starts to behave like a classical wave. And this is indeed the behavior of a classical wave, because all we did is to solve the classical field equation. So that whole idea that somehow millions of atoms would work together to behave like a classical wave is manifested in this picture. And in addition, this picture tells us that this system has zero viscosity, no friction, and there's a topological protection on this system. So these three highly non-trivial things are all there in front of your eyes in these pictures. So I find this actually really, really amazing. And that's what we can describe with this quantum field theory, or rather classical field theory, to describe the behavior, collective behavior of millions of atoms working together. So just for you to appreciate how incredible these pictures actually are. I hope that makes sense. Any further questions on this? Okay, so I talked about this, the Bose-Einstein condensate, when you have this lambda to be repulsive interaction with positive chemical potential. Because potential is repulsive, you need to put particles only by making chemical potential positive. So repulsive potential always try to minimize the number of particles, but by making chemical potential positive, you actually gain energy by putting in more particles. But eventually that gets limited because the repulsive interaction starts to win. And that's exactly this idea of this potential well we talked about, this picture here. So once you have this potential, then you would like to put more particles in because of this positive chemical potential. And indeed, potential starts to go down quadratically. But once you put enough particles in, then this repulsive potential starts to win. Then you have a sort of a resistance in order to put more particles into the system. And you find somewhere in the middle. And that's this bottom of this potential. That's how we understand this potential here written in terms of the field. And that's why we find a stable solution at the bottom of this potential with a finite density, which turns out to be the coherent state of particles. So that's what we talked about before. So one can ask the question of what happens when you actually flip the sign of this quadratic term. So because the meaning of this quadratic term was this delta function repulsive potential among particles, we have shown this by comparing the language in QFT versus language in multiparticle quantum mechanics. And this lambda term indeed gave us this lambda delta function potential in multiparticle Schrodinger equation for the multiparticle the Schrodinger wave function. So we know what this meaning is. This is a repulsive interaction. So when you actually make this attractive, then you have a weird situation, because you do gain energy by putting more particles because of positive chemical potential, but there's no resistance to it. Now that the potential is attractive, then you start putting more and more particles, and there's no limit to it. Indeed, if you just plot this potential with negative lambda, you'll find this shape instead. So it starts to go down quadratically, but then this lambda is also negative. It goes down even further, now quartically, and just keeps going down forever. So if you put a particle here, what would happen is obvious. It starts to roll down the hill It just keeps going, and there's no stable point to stop. And when psi is going down the hill, namely psi is becoming bigger as it goes down this potential, psi dag of psi, that's a number density that keeps growing, and eventually number density becomes infinite. So in the finite system, what it means then is that you have originally a stable BEC, but then once you flip the sign of lambda, it starts to go, it collapses to a point with infinite number density. And once things collapse, then there's a bounce that will let the system explode. So that's what you would expect. So density goes to infinity and shrinks to a point, collapses a point, then it bounces back, and boom. This is what is called the Bose Nova. And you might know this idea in astrophysics called the supernova, when a star, somewhat bigger star compared to our sun, starts shining for thousands and millions of years. But at some point, it uses up all the fuel for the nuclear fusion process at the core of the star. Then it can't produce energy anymore. It can't support its weight. So it starts to collapse because of the gravitational pull. And once the core of the star collapses, the outside gets bounced and produces such a huge explosion of the star that a single star outshines the entire galaxy. And that is the phenomenon called the supernova. So this is actually named Bose Nova because it's kind of similar to that. It's Bose because it's a Bose-Einstein Condensate. But once you actually flip the sign of this quartic potential, which you can do experimentally in the laboratory by cleverly choosing magnetic field and electric field, what used to be the repulsive potential between the atoms, you can tune it to make it into an attractive potential all of a sudden by dialing the magnetic field. In between is called the Feshbach resonance, where you have no force between atoms. So you can dial from repulsive force to an attractive force. And once you do that, this collapses a point, then goes boom, and that's the Bose Nova. And you can look up this website yourself later on. You can download the slide and click on this link. So Bose Nova is actually a demonstration that it was really this repulsive potential that kept the BEC stable for a long time, even though it would eventually decay, as you saw in this data. But once you actually make the system to have attractive force, then you have this instability against collapse. It collapses the point. That's how the field psi rolls down the hill. The psi becomes infinite. Psi dag of psi, number density becomes infinite at the center. And then the whole system bounces back in this explosion, hence Bose Nova. So this is really cool. And this is indeed some people indeed do in their laboratories by dialing magnetic field. You switch from repulsive to attractive, then collapse and explosion, and Bose Nova. Okay, I hope you like this. Any questions about this?
I have a quick question. Can we get another stable solution if we keep the attractive potential, but then also flip the chemical potential to be negative?
No. So again, going back to the previous slide, oops. If the chemical potential is negative and the quartic potential is also negative, then what you have is this potential just flipped upside down, right? So then your origin looks kind of stable, but not really stable because it's local minimum, and then it would tunnel out eventually. So that is what is called the metastability. So it is stable for a while, but eventually the system will tunnel out and go to the infinite density by just collapsing the whole thing into a point. So it's not really stable, even when you have the negative chemical potential, which stabilizes just the origin, but doesn't stabilize the whole system. Okay, thank you for asking the question. So asking those questions, what happens in this case, that case, really is a good way of thinking about getting the big picture on what's going on. So I appreciate that question. Any other questions? Everything okay? All right. So Bose Nova, that's something you can really observe in your laboratory. There you go, right? Let me do that again. Explosion. Once again, I like this. Explosion. All right. But what I'd like to also point out that you can actually have a completely stable superfluid. And this is the one that had been discovered actually much before this cold atom BEC had been created in the laboratory, just because of technological difficulties. Creating this nano-Kelvin dilute gas of cold atoms was a technologically difficult thing. And Steve Chu, who was a student in Berkeley, actually invented this laser cooling technique and got a Nobel Prize for it. And he actually came back as a faculty member in a department for some period of time, also was a director of LBL, but now he moved to Stanford and he's a professor there. So he's one of the offspring from Berkeley and is a Nobel laureate. And he even did the energy secretary in the Obama administration. And he created many of the environmental policies in the Obama administration. So I don't know your political bent is, but at least we had this kind of a person on our faculty. And so that's how this Bose-Einstein Condensate became possible. But a long time ago, this started, I think, in 1930s, the people start to cool liquid helium. And at the normal atmospheric temperature, it never solidifies. It stays liquid all the way down to 0 Kelvin. That's very special about helium-4. And because it never solidifies, you don't have this problem that the BEC gets lost against the solidification. So superfluid turns out to be totally stable, and you can observe it for a long period of time, like a year. And then they can see a really macroscopic experiments with them. And this is one of those weird things. So here you have a liquid helium-4 in the beaker. This is already low temperature. But once you cool this temperature further down, at some point, you have a phase transition. You see boiling behavior and becomes perfectly still when it becomes a superfluid. And this beaker has a bunch of tiny holes in them. And when the fluid has a friction, holes are so tiny that it doesn't flow through these holes. But after phase transition becomes a superfluid, loses viscosity, then fluid starts to escape through the tiny holes at this bottom of this beaker. And that's what you're gonna see in this BBC video. For a phase transition point. Then becomes superfluid. So that beaker didn't have the holes, but next one does. So got a bunch of holes there. Because there's no friction. And that's weird things. It climbs the wall and escapes this beaker. So you see dripping. And you have learned the new radical theory, and that's the QFT. So once you know QFT, you can describe the superfluidity of helium-4, liquid helium-4 as well. It's just the Bose-Einstein condensate. There's one little caveat though. So dimensionless parameter in perturbation theory is rather large, so we can't trust perturbation theory to full extent. But all the qualitative behavior can still be described by the classical field equations, just like we have been doing with BEC, and understand these phenomena, namely the zero viscosity flow superfluidity. And so these pictures and the videos are really amazing. And when I looked up the superfluid on Google, this is the first video that came up. So that's why I'm showing it. I really hope that there's a newer version of this with a better resolution and better quality picture. I didn't find it, but if you do find it, let me know. I'd like to replace this with something newer. But it's still, I hope you got the point that once you cool liquid helium, you have a phase transition where you saw this boiling going on. And below the phase transition temperature becomes perfectly still. And if we have pores at the bottom of the beaker, then the superfluid starts to flow through tiny, tiny holes because there's no viscosity anymore. And it can even climb the wall and escape the vessel. It can have this frictionless fountain. So it does all these amazing things. So that's the idea of superfluid helium-4. And this is actually used, if you like, in the Large Hadron Collider at CERN. When you cool the magnet to a low temperature of the superconductivity, we get to that idea also soon. But because the helium-4, so everything is now dipped in the superfluid helium-4, and because the fluid has no friction, it can just go anywhere in the system, again, without any friction, and can really fill up the entire system. So it's ideal for the purpose of cooling something to a very low temperature. And so the helium not only is fascinating subject of its own, it's also useful for other purposes. And if you go to, for example, a hospitals, and if you would like to do a MRI, medical resonance imaging, then also you need to have a superconducting magnet, and you need the superfluid helium-4 to actually make that happen. So you don't see that actually in front of your eyes because it's all sort of built into the system, but that's actually what's going on. And the helium is getting more expensive, partly because of that. Any questions about this? Anyway, isn't that amazing? So what's going on here? Let me sum it up. So first of all, phase transition. So this is actually the heat capacity as a function of temperature. And this is already low temperature of 3 Kelvin, not nanokelvin. So it's compared to nanokelvin, it's much higher than that. But this is what they even managed to do back in 30s because of this. And when the temperature gets lower and lower, at some point, heat capacity blows up. So there's a singularity. And this is what is called the second order phase transition. So this is the heat capacity. So it's a derivative of the free energy. So blowing up means you have this the kink in the behavior of the free energy, right? So that's how this the phase transition appears, and then starts to go down, and to almost zero heat capacity if you go to a very low temperatures, and that is the meaning why the fluid becomes totally still. And in terms of the phase diagram, this is temperature, this is the atmospheric pressure, 1. This is higher pressure. Only when you go up to something like a 2.5 atmospheric pressure, helium can solidify. But at the atmospheric pressure we live under, even if you lower the temperature, it never becomes solid. You go from normal liquid to super liquid, but never becomes a solid. So there's no way that BEC gets lost now, because there's no instability against solidification anymore. So that's why you have this, macroscopic long time experiment. You can manipulate this superfluid and create fountains and all that stuff, thanks to that stability. So this superfluid liquid helium-4 is a completely stable Bose-Einstein condensate. And that happens at a few Kelvin temperature. Again, you can just plug in numbers by identifying sort of typical distance between the helium atoms and liquid. Let's say that's 3.5 angstrom. And you make sure that the typical distance, it becomes comparable to de Broglie wavelength, which you compute the temperature. So for a given temperature, you have the kinetic energy given by half kT each, equipartition theorem. So that gives you an estimate of the momentum at that temperature. And once you have the momentum, you put that in de Broglie's relation to work out the de Broglie wavelength of the particle with a definite the momentum. And that is given by this h over square root mkt. So you equate this to the typical distance, 3.5 angstrom, to work out what T that should be, and you find it's of the order of 1 Kelvin. So indeed, it's about 1 Kelvin, more precisely 2.2 Kelvin. That's when the phase transition happens from normal liquid, which is just a collection of a bunch of atoms, to a superfluid, where all these atoms start to overlap with each other and start behaving like a classical wave. The same idea we talked about for this cold atoms, but now this is a macroscopic fluid. So that's the idea of the superfluid liquid helium-4. So any questions about this?
Can you just
Okay,
quickly explain again why we don't need to go to nanokelvin? Is it because of the separation between the helium atoms is a lot smaller than normal?
That's right. So in the case of the cold atom BEC, you wanted to keep atoms somewhat far apart from each other because you don't want to risk solidification right away. You don't want atoms to bunch up together. So you want to keep some distance among them. That's why it was very dilute gas of atoms. So I kept the distance like 1,000 angstroms or something. And that's why you needed to go down to much, much lower temperature for this phase transition to take place. But here, there's no concern about solidification. It stays fluid all the way down to 0 Kelvin. So you have just normal dense liquid by cooling the helium under atmospheric pressure. Then it does turn into superfluid at a much higher temperature of Kelvin. That's when the de Broglie wavelengths start to overlap with each other. Thanks for asking that question. Any other questions here? And if you go to more advanced courses on QFT, then you can even start to compute this singularity, how quickly that actually blows up, and what is the power in terms of the temperature around here. It's called the critical exponent. That becomes also something you can predict out of quantum field theory. And so things can become much more quantitative than what we are doing here. I stay more qualitative because it's actually beyond perturbation theory now that the coupling is not less than 1. But nonetheless, you can understand this at least qualitatively using this quantum field theory picture. And so here you already see the situation is different from Bogoliubov spectrum. If you remember the Bogoliubov spectrum, it starts linearly and then keeps going up quadratically. And that was the Bogoliubov spectrum we worked out with the classical field theory. This is the data for liquid helium superfluid. And the way you can see this is by sending in neutron. You know the neutron that went into the system, you know its energy and momentum. Neutron gets scattered, you measure its energy and momentum. So you must have created an excitation to the system that corresponds to the difference of energies between initial and final state neutron and momentum difference between initial state and final state neutrons. Then you can just plot it, the energy as a function of the momentum transfer. So this is the spectrum of elementary excitation of the superfluid. It goes up linearly, so that part is the same, but it comes down once, then eventually starts to go up quadratically. You have a dip, and this dip has a wrong name called roton. Early on, people thought that this was the vortex of fluid going around. That was not the case, but people thought it that way and named it roton, but the name stuck. So it's not rotating fluid, but nonetheless, you have this dip. And having this dip gives you this idea called the critical velocity. I'll come back and talk about this in a moment. But anyway, so this is a spectrum. You already see that the classical field theory analysis we have done before doesn't quite work anymore. This is a strongly coupled system. There's something beyond perturbation theory that's going on in this system. But nonetheless, you can do the estimates of what kind of elementary excitations you may have, knowing the various quantities of typical distance mass of the helium, typical wavelength of the excitation, and estimate the energy of these excitations, and it more or less work. So qualitatively, you can still get a good description using classical field theory. More details don't quite work out because this is beyond the perturbation theory. So it's more difficult to understand helium-4 because of that. That's why I discussed the BEC of cold atoms first, where perturbation theory is perfectly valid. We could work out the Bogoliubov spectrum of elementary excitation. Now, it's a little bit more complicated and difficult to deal with. But anyway, so do you, I hope you get this idea of elementary excitations. Okay, so now that there's a dip, there's an interesting argument by Lev Landau. What is the maximum possible velocity of the superfluid? And this is the criteria he came up with. So if you think of viscosity that would terminate superfluid into a normal fluid, then what you're looking at is the flow of this fluid with velocity v around some macroscopic object I drew with this black circle of mass capital M. And if the fluid velocity is too high, then it may no longer behave as a superfluid. It might having some viscosity. But the idea of viscosity is that it's actually microscopic excitations, right? For example, if you have viscosity of water heating something, then heating will produce basically heat in water, which is the microscopic excitations of the water molecules. So turning this macroscopic energy of the flow into collection of bunch of microscopic energies is the viscosity. So the question here is that when, at what speed, this flow next to this macroscopic object would start to produce these microscopic excitations we have seen on the previous slide. And that idea would give you a criteria for the critical velocity beyond which superfluid starts having a friction and no longer superfluid anymore. And this is what he did. First, you think about this macroscopic obstruction, and you have a superfluid around it. But again, using this idea of Galilean invariance, I can go to the rest frame of the fluid instead, and think of this obstruction moving inside the fluid, and physics is supposed to be the same in either reference frame. Then you ask in the following question, can this macroscopic object M, now it's moving with speed v, slow down by creating a microscopic excitation around it? So it used to move with speed v, but now it's moving with speed v prime, slow down a little bit by spitting out a microscopic excitation. Is that possible? And of course, that needs to conserve energy and momentum. And we have learned this spectrum with this dip in the middle. So can we satisfy energy momentum conservation using this spectrum? So initially, I have this macroscopic object moving with speed v, got kinetic energy half mv squared. If it slows down to velocity v prime, new kinetic energy of this macroscopic object is half mv prime squared by spinning out this microscopic excitation with energy E. That's the energy conservation. You have to satisfy momentum conservation too. Initially, this macroscopic object had momentum mv. Now that it's slowed down, it's down to mv prime. And I'm making the assumption that everything is one-dimensional here. So then the microscopic excitation you create should carry momentum p away so that the momenta are also conserved. Can we satisfy these conditions? So that's the question we should ask. Now, of course, the M is a big macroscopic object, so M is very big. So let me first look at the second equation, divide this by M, then you find this initial velocity V and final state velocity V prime is related by this equation. V prime is V losing P over M. Now I substitute this V prime into the first equation of energy conservation. So V prime squared is now V minus P over M squared. And I expand this out, MV squared minus 2VP and P squared over M. So I already multiplied this capital M on top of the square. So that's the energy of the final microscopic particle object. and the energy of the microscopic state, E. So can we satisfy that? But now that this capital M is meant to be M big, it's a macroscopic object, I can ignore this piece suppressed by 1 over M relative to everything else. The first order thing is the biggest thing in this equation, half mv squared, is common to both sides, so I can just eliminate them. So I lost this biggest piece, order M. Then I have pieces that is order M to the 0th power, and have the piece 1 over M. So clearly I can ignore the piece 1 over M and balance out pieces that is M to the 0th power between this momentum V and energy E. Then you find this linear relation that E has to be minus Vp. So you draw the straight line as a function of P. And when it touches this curve of the energy of the microscopic excitation, then you can satisfy energy momentum conservation. If the velocity is lower than that, then this 2Vp never gets up to the level of satisfying E. So you can never satisfy this condition. Therefore, you cannot create microscopic excitation. Therefore, there is no viscosity. So that's the underlying reason why superfluid helium does become a superfluid with 0 viscosity, because you cannot dissipate energy into a bunch of microscopic excitations. If you go back and think about the case of the dilute gas atom, then that's even better, because it starts out linear and smoothly goes over the quadratic without any dip. So the critical velocity turns into just the initial slope of the Vogel-Ribot spectrum. So there's no dip, so it's easier to satisfy that. But in the case of helium, because of this dip, you start to lose superfluidity against this roton excitation earlier. So critical velocity turns out to be lower. But nonetheless, up to that velocity, you expect superfluid to stay superfluid. And that's this beautiful criteria Landau came up with. So then you satisfy this equation of the linear relation that intersecting this roton spectrum, which becomes possible only above the critical velocity. If you think of the normal fluid, then elementary excitation is just the motion of individual molecules individually, which means the energy goes quadratically with momentum, p squared over 2m. That's something we are all familiar with the classical mechanics. Then even with the infinitesimal velocity, you always find an intersect. So critical velocity is therefore 0. Even for a tiny motion of this macroscopic object, you can lose energy into microscopic excitations. Hence, there's a viscosity. So now everything makes sense. For normal fluid, the particles move individually in a fluid. Energy is quadratic with momentum. Therefore, you can satisfy this Landau's criteria already with a 0 velocity. Critical velocity is 0, namely for a very slow motion of the fluid, you can lose energy of the flow into microscopic excitations, hence viscosity. For a superfluid helium-4, only when you get up to this critical velocity, this macroscopic motion can start to lose energy into microscopic excitations and gain viscosity. So up to that critical velocity, it remains superfluid. And for the dilute gas of cold atoms, then it's even steeper. And you have to get up to this initial slope to lose the flow into microscopic excitations. So that's how you can understand now all phenomena on a single footing, and hence Landau criteria is a really powerful argument to understand why 0 viscosity can happen given a excitation spectrum of a given system. Okay, I hope that makes sense. Any questions about this? Word of caution, though, is this discussion is still somewhat idealized. If you have, for example, the obstruction, which is like a square, you have an edge, and flow might create a turbulence around it. So it turns out that even before reaching this critical velocity, you might start losing the superfluidity because of this rather turbulent behavior. So this is definitely an idealized discussion, but at least gives you a sense of why viscosity works, namely losing energy of the macroscopic flow into individual microscopic energies. That's the origin of the viscosity. And when viscosity should not be there, when you have this linear rise of the excitation spectrum, so that up to a critical velocity, you cannot create microscopic excitations by conserving energy and momentum. Okay, any questions about this? Is everything okay? All right, then the same idea also applies with the vortices. Once again, we get the same classical field equation and hence same solutions. This is actually what the Dick Packard, department did a long time ago. So he created a superfluid helium, and now that's something you can really put in a bucket. And he rotated the bucket and observed this triangular lattice of vortices. And so you see 2 vortices, 4 vortices, 1, 2, 3, 4, 5, 6, and so on and so forth. So this is something you can literally do by rotating a bucket where the superfluid helium is fitting, and you observe this lattice of vortices. So same physics, totally different systems, totally different regimes of the coupling. So one is weakly coupled, this one is strongly coupled, but this is the power of physics. Once underlying equations are the same, you observe the same phenomena, and that's really the origin of fun of physics. The same equation is rather universal, describing many different systems, and hence lattice of vortices. Okay, any questions about this? Everybody's okay? Good, I see nodding. And then I'm basically done with the discussions of Bose-Einstein condensate and move into the discussion of fermions. So let me pause here again. Are there any questions you might want to ask about this whole issue about bosons in general?
Yeah, I have a quick question.
Go ahead, Adi.
Do we take the interpretation of the quantum field, or at least the magnitude squared of the quantum field, as number density, or as matter wave? Is that do we carry that idea with us as we go on, or do we kind of leave that only for the BECs?
That is what works for the BECs. So for the normal temperature and the negative chemical potential, you actually found the minimum potential at the origin, because the negative potential would let the potential rise quadratically near the origin. So psi was be sitting at the origin. There's no expectation value, therefore it's not a coherent state. That would correspond to this number 0 state in harmonic oscillator sitting at the center in a phase space. So then you create the particles with the creation operator in a normal fashion in a Fock space. So then you're talking about collection of bunch of particles, not behaving collectively, but you see this collection of individual particles. That's a much more normal behavior. So that's actually the quantum field theory. The weird thing is that when you do classical field theory, you end up describing this highly quantum state of matter, which happens to be a classical wave. That's where the concept of the classical and quantum got switched. Concept of particle and wave got switched, but it doesn't make sense because we're describing the dual nature of the quantum physics anyway. And so the negative chemical potential case is in some sense more normal, that you have a field which you quantize, get particles out, and you're looking at the collection of individual particles that way. Okay, does that answer your question, Adi?
Yeah, thank you.
Very good. Any other questions about bosons in general, now that we are switching to fermions? All right, so we have discussion section later today again, so you are welcome to come and ask more questions about that. Now we move to fermion, and many of you insisted to know about fermions already from the very early on, so let's just dive into it. So biggest difference from fermion and of the fermion from bosons is the Pauli's exclusion principle, as all of you know, namely that you can put only one particle into a same state. For the case of bosons, you can put many bosons occupying the same state, and that's indeed what happened with the Bose-Einstein condensate. You have a macroscopic number of particles occupying the zero momentum state in the form of the coherent state, and so that's possible only because they are bosons. And for bosons, we had this familiar commutation relations among the creation and annihilation operators. But now we have to think about how to describe fermions instead. So as you all know, only one particle can occupy a state in the case of fermions. So occupation number is either 0 or 1, never 2 and beyond. And that's the idea of Pauli's exclusion principle. So the question is, how do we describe that? Using field, and entire formulation of the field hinged on the harmonic oscillator. So what we are looking for is some kind of fermionic version of a harmonic oscillator. We still want to have creation annihilation operators because we're dealing with QFT, but we need to make sure that the same state cannot be occupied more than once. So is there a version of a harmonic oscillator that does that? And it turns out that this is actually a very simple answer to this question. All you have to do is replace commutation relation by anti-commutation relation. So the commutator of two operators A and B is AB minus BA, as you all know. Anti-commutator is AB plus BA instead. That's the only difference. So you have creation annihilation operators, which now satisfy these anti-commutation relations. BB dagger plus B dagger B is 1. BB plus BB is 0. B dagger plus B dagger is 0. But now you see the crucial difference here, because B dagger plus B dagger, which is just twice B dagger is 0. Namely, B dagger times B dagger is identically 0. Therefore, you cannot create particles twice. If you have state with 0 number of particles, you can create one particle by acting B dagger on it. So that's the state 1. But when you act B dagger once again, that vanishes because B dagger times B dagger is identically 0 as an operator. So you cannot occupy the same state more than once. And that's exactly what you want for fermions. So this actually turns out to be a simple answer to your question. How do we describe a fermion using harmonic oscillator? So now we have this weird kind of harmonic oscillator where creation annihilation operators satisfy anti-commutation relation. You just change the minus sign to plus sign. But that actually turns out to do the job completely because now you know B dagger twice is identically 0 as an operator. Therefore, you cannot occupy the same state by two identical fermions. So that's the way we would like to build our formulation again in quantum field theory. So any questions about this idea?
I kind of have a question.
Oh, go ahead, Gerardo.
You had said that for the anti-commutator, B dagger cannot act twice to create a particle of 0. Can't you make a similar argument for A dagger A on the top? Or
well, in this case, A dagger minus A dagger is 0. So this commutator is trivial. It doesn't give us any constraint on how A dagger should behave. And same here, AA minus AA is identically 0, of course. So it doesn't give us any additional ideas on how A should behave. So you don't get a constraint that A dagger twice is 0 because of the negative sign in between. But now that it's a positive sign, two terms would add up. That's why this ends up being twice B dagger, which is supposed to vanish identically. And thus you get this additional constraint now that B dagger twice is identically 0. So that's the difference. Does that answer your question, Gerardo?
So it's different because in the first one, it's not necessarily 0 because we set it 0. It's 0 because A dagger minus A dagger is 0.
Right.
And on the bottom, we would say B dagger plus B dagger is twice, but it's 0. So I'm gonna buy that. Okay, yeah. I think so.
Okay. So I admit that this is weird, but nonetheless, that's the commutation relation. And mathematically, once you have this anti-commutation relation that defines your algebra, then everything is built on this and everything is well defined. So that's the idea. So once you have these canonical anti-commutation relations that fixes the algebra of creation relation operators, and you know your Hilbert space consists of only unoccupied state and singly occupied state, and nothing else is there. So that's how we realize Pauli's exclusion principle. And whenever I teach quantum mechanics class, I denounce this name. You know, we're supposed to be diverse, inclusive, the equitable society, and we don't want to exclude anybody. So this is actually a pretty bad name. So I've been proposing to rename Pauli's exclusion principle to diversity principle. And it makes sense, right? All the fermions want to be different from each other, spread out and occupying diverse set of states. So I believe this is the right name for it. But so far, people didn't buy into this name yet. So please advertise this name. And so this is my proposal to rename Pauli's exclusion principle to Pauli's diversity principle. Okay, let me stop here. I ran out of time. So I start to build QFT out of this new weird harmonic oscillators are using anti-commutators and see how field theory actually ends up looking like at the end of the day. Right, that's it for today. Any questions? All right, so as I said, we have discussion, the office hour later today from 5. I post a new homework, the regular homework later today. And next week, it will be the 1 week take home midterm. Okay, all right, have a nice weekend.
Thanks, Professor.
Bye.
Thank you, Professor. Bye-bye.